Hi guys, this video is going to be a practice problem for a heating curve of water total energy calculation. It's actually found at the end of your heating curve lab. It's the very last problem. It's number 16. So in this problem, we've got a 75-gram ice cube removed from the freezer, and its temperature in the freezer was maintained at -10°C. We want to know how many kilojoules of energy total are needed to raise the temperature of that water to 55°C. Whenever I give you one of these types of problems, you need to sketch a heating curve. So let's go ahead and do that. And then this temperature starts at -10°C. So this is my temperature on my y-axis. We're going to increase the temperature to 55°C. And there's going to be an important temperature between -10 and 55°C, which for water is the temperature where ice melts, and that is 0°C. So we actually have 3 sections to this particular heating curve. There's section 1, here's section 2, and then all the way over here is going to be section 3. So we're going to have a Q equals MC delta T from -10°C to 0°C. And we're going to have to use the specific heat for ice for this section. I'll show you where that's located in a moment. Then we're going to have to do a phase change using the delta H of fusion for section 2. And then we're going to be able to use a Q equals MC delta T with the specific heat of water, which we're very comfortable with using because that's what we've been using all units. We actually have 3 sections we're going to have to do individually and then add up. And all of these specific heats for ice, water, and heat of fusion, which we'll need for this. If we backtrack a little bit in our heating curve lab, there's a chart here which you'll have on tests, you'll have on quizzes, so that you'll be able to access that information. So I'll pull the specific heat of ice and the specific heat of liquid water and the heat of fusion onto our next part where we start calculating the individual parts. All right, let's go to our next section here in our practice problem and break down not just our great heating curve diagram here. Let's do this section by section. So section 1 is set from -10 to 0°C. We have a delta T. So in this part, we're going to use Q equals MC delta T. And again, we're going to use the specific heat of ice, which is on the previous page. So to find the energy here, my mass is 75 grams. My specific heat of ice is going to be 2.06 joules per gram degrees Celsius. And remember, delta T is temperature final minus temperature initial. So I am going to do temperature final 0°C minus -10°C. Running out of room there. So this is going to be minus a negative, or I'll end up with a positive energy input because energy is going into the ice cube. It's going to be positive. So when I do 75 times 2.06 times 10, I end up with a value in my calculator. I've got 1,545 joules of energy. Remember, there's 1,000 joules in 1 kilojoule. So if I divide by 1,000 or move over my decimal point, 1, 2, 3 places, I end up with 1.45 kilojoules. That's how much energy I need to go from -10°C to 0°C. The reason I changed to kilojoules is I need to total up all 3 parts into kilojoules at the end. So I'm just going to do it now. Put a box around it so I know where it is. All right, section 2. There's no delta T here. So if I have a delta T of 0, that would make my energy input 0. But we know energy is going into the system here because the energy is moving the solid particles further apart. the potential energy is changing. I'm getting a liquid. So what I'm going to have to do is I'm going to have to use the delta H of fusion, which is recorded on the previous page. So delta heats of fusion are given in kilojoules per mole. So I'm going to have to take my grams into moles. So review grams to moles. There are 75 grams of water. I want to know how many moles that is. There's 18 grams of water in 1 mole of water. Cross multiply, divide. I ended up with 4.16 moles of water. Now I'm going to do my next step using the delta H of fusion, which on the previous page is recorded as 6.01 kilojoules per mole. So I know if I have 4.16 moles of water, I want to know how many kilojoules that is. I'm going to take my delta H of fusion, which is over here, and pull it into my proportion and say for every 1 mole of water, there's 6.01 kilojoules required. Now I can cross multiply. I could divide by 1, but it's going to end up with that same value. I'm already in kilojoules. So when I put this in my calculator, I'll round sig figs all the way at the end. I'm going to keep everything right now. I end up with 25.04 kilojoules of energy. Okay, that's step 2. Back up a little bit. I know it takes 25.04 kilojoules of energy to completely melt that ice cube. But I don't want to just melt the ice cube. I want to raise the temperature of the ice cube up to 55 degrees Celsius by adding heat over time. So step 3 is going to be back to another Q equals MC delta T, but now I'm focused on liquid water. So mass in my ice cube still 75 grams. The specific heat of water, 4.18 joules per gram degree Celsius, liquid water. And then T final minus T initial, 55 degrees Celsius minus 0 degrees Celsius gives me 55 degrees Celsius. 55 degrees Celsius. All right, so I'm going to do 75 times 4.18 times 55. That will give me, in a unit of joules, the answer of 17,242.5 joules of energy, or that equals 17.2425 kilojoules. Move that decimal 3 places over to the left. That's a whole lot of energy to raise that 55 degrees ice cube. So now I've got these 3 parts. 1.54, 5 kilojoules, plus part 2, 25.04 kilojoules, plus part 3, 17.2425 kilojoules. I'm going to round to 3 sig figs at the end because that's how many sig figs are in my delta T. So here's going to be my total. I can finally answer this question. All right. It's going to be part 1 plus part 2 plus part 3. And when I did that in my calculator, I ended up with 43.8 kilojoules of energy. I'm finally going to round to 3 sig figs because, again, we're getting 3 sig figs from my temperature reading. So here is my final answer once I add up all my individual sections of the heating curve. So when you do these problems, sketch yourself a graph. Think about where you start, where you finish, where the plateaus are. For water, it's at 0 degrees and would be at 100 degrees, but this problem didn't ask for it. You'll have other problems that do. Do each individual part, show all your work with units, and then your total will be all the parts added together, usually answered in kilojoules.